Okay, so like I said, the next item on the agenda is to actually look at real solutions to the Friedmann equation for the different cases that we've discussed. So let's just write out the Friedmann equation again. Okay, so before we get to the solutions with different types of components, one can just start perhaps by wondering what would happen if I have a universe with nothing in it, just an empty universe. How would that behave? And if you look at the equation, then this term becomes 0, and the Friedmann equation reduces to this form. Now, one possible solution would be to have kappa equal to 0. So that gives you 0 exactly on this side here, and the only thing that matches that would be to have a dot equal to 0. And that's a good thing because that's actually static normal Minkowski space of special relativity, right? That's a static Euclidean space with no curvature, and a static space must of course have a dot equal to 0. However, it's not a description of the universe we live in because we know that the universe is an expanding system. So if a dot is different from 0, then this term must be positive. And the only way that can happen is if kappa is equal to -1. So that will give us, if you want, a normal expansion of the universe. So then I get a +1 here. Then I multiply through with a squared. Then I get a dot squared equal to 1 divided by r squared. And of course I can now integrate that, take the square root and then integrate it, and then I find a of t is equal to plus minus t divided by r plus some integration constant. So now I get a universe that either expands or contracts linearly with time, which perhaps is also what you'd naively expect, right? Because you have no source term for gravity, there's no energy density, and that means in this very simple case, if I start the universe out expanding, then it just keeps expanding forever at the same rate, because what else could it do? Or if it contracts, it's the same thing again, right? So that's of course not a very physical example because we know there's energy density in the universe. Now, other simple analytic solutions you can derive by explicitly taking the kappa equal to 0 case. So that's the same as saying that the total value of this density parameter is exactly equal to 1. And this is something that you've heard about in other parts of the course, which Max has talked about. Of course, there's plenty of observational evidence that, yes, indeed, this is true. The total value of omega is exceedingly close to 1, and therefore it's natural to see what kind of simple solutions are there in this limit. So in that case, the Friedmann equation also becomes quite straightforward because now we have no curvature term. And then it's just simply a question of plugging in the 3 different solutions that we looked at, namely matter, radiation, and cosmological constant, and see what comes out. And you can do that. The way you do it, of course, is completely identical to how you would normally solve such a first-order differential equation, right? You would separate variables and then you would integrate. And then what you find is that in this case, it becomes proportional to time to the 2/3. Here it becomes proportional to time to the 1/2. And here, interestingly, the expansion is exponential, right? Because now you just get a constant term and the differential equation would be a dot equal to some constant times a, which of course has an exponential solution. In these cases, you get power law solutions. So intuitively, what you get is something where if you have matter that dominates, then the expansion is slower than in the empty universe. So indeed, matter, yes, acts as a source of gravity and slows down the evolution. the expansion of the universe. Radiation actually, surprisingly perhaps, slows down the evolution even further. But that's because pressure is a source of gravity. It's completely different from what you'd normally think of pressure in classical mechanics, right, where pressure counteracts gravity. Here in, in the Einstein equation, of course, it's a source of gravity. It acts as a source term for the gravitational field, and that means that gravity becomes stronger for the same amount of energy density in a universe with radiation. Now here, of course, you have a runaway solution, right, because the energy density remains constant at all times. So even though you expand the system, the energy density remains the same. And weirdly enough, of course, this also leads to something which is quite strange when you first see it, namely that the total energy in a co-moving box actually grows very rapidly. But of course, it's due to the negative pressure. So in fact, the universe likes to expand more the more it grows. I mean, normally in a thermodynamic system with positive pressure, if you expand it, then it cools off and pressure drops, and then you reach an equilibrium. Here is the runaway solution because you flip the sign of the pressure term. So it's completely different. Okay, but that's basically all there is to it. Now, of course, in the most general case you can think of, you cannot actually solve the Friedmann equation analytically. If you put in both radiation and matter and cosmological constant and curvature, there's no very simple closed analytic form of the solution to A of t, and you'd rather do it numerically, but that's not a very difficult equation to solve numerically, and you can do it very cheaply and very precisely.